Okay, let's continue. In Chapter 5, RSA asymmetric encryption algorithm. Regarding the different attack, we are now at the chosen ciphertext type ciphertext attack. This attack is well known, and RSA is vulnerable to this chosen ciphertext attack. We will see together how the attacker could choose ciphertext and then get decrypted plain text back. And here it's really based on a kind of cryptanalysis that is specific to the function of RSA, how RSA is done. So the idea here is that it comes from the fact that if we encrypt with the public key a message M1 and then we multiply the encryption of this another message M2 using the same public key, it's similar to the encryption of the multiplication of the plain text. So this is a kind of what we call multiplicative encryption. It's a homomorphic encryption. It's a kind of multiplicative homomorphic encryption. We will see this by the end of the course if we have time. So given this characteristic, this is one of the characteristic of RSA. So that's why, based on some cryptanalysis, so an attacker could decrypt plain text using this characteristic. For example, let's say the idea is that choosing ciphertext. So how the attacker will operate. So assume that the attacker intercepted a kind of ciphertext. Okay, so the ciphertext is the encryption of a certain plain text M and encrypted using the uh, public key E mod N. Okay, and then at this level, what the attacker will do is the attacker will try to multiply this ciphertext with another term 2 and also to power E because this is the public key and mod N. So he obtained a certain value X. Okay, and now assume that the attacker is able to communicate with the victim using X because assume that X is something legible for the victim. And in this case, the attacker will submit X as a chosen ciphertext to the victim. The victim will work on X because he assumes that X is coming from a legal person, the attacker. So the victim is not aware that within this X there is some ciphertext and the attacker try to decrypt them. So typically, if the victim will decrypt the X, okay, and then we'll send Y back to the attacker. So in this case, the attacker will receive Y. Y is X to power D mod N. Okay, so in this case, X to power D mod N, the attacker receive Y. Okay, and we can see what's X. X was C, the ciphertext the attacker want to know, and multiply by T to power E. So it's C mod M times T to E mod N. So it's C is the ciphertext, the plain text to power E, and 2 to power E mod N, it's similar. So in this case, if we want to have, it's like 2M power E, it's like the encryption of 2M. The encryption of 2M is Y. So the encryption of 2M is Y, and in this case, we encrypted here 2M. Okay, X is 2M. If we decrypt this 2M, we obtain Y, In this case, y equal to m. So in this case, when receiving y, just the attacker will deduce m because it's 2m, it's the double of m. So this is a kind of attack, and we consider that RSA is vulnerable to this kind of attack. This characteristic will be used for homomorphic encryption because it will be very useful to have the encryption of the multiplication of certain number is equal the multiplication of the encrypted number. So we will see this characteristic after. So this is regarding chosen ciphertext attack. You can reuse it also, okay? So what about other public key crypto system? I will try to finish this chapter, and after that we will do all exercises regarding RSA and the other one. So the other public key crypto system, remember we have Diffie-Hellman, and we say that Diffie-Hellman will be used mainly for the key exchange. It's very useful for the key exchange, and it's really a simple public key algorithm for key exchange. The objective of the algorithm is to enable two users to securely exchange a key that can then be used for subsequent encryption of message. So they exchange the secret key, and after that they can use another encryption algorithm but using the secret key. So the algorithm itself, as we said, is limited to the exchange of the secret key. So with Diffie-Hellman, we are not doing an encryption like, for example, RSA or, for example, other encryption algorithm. The essential here is just to exchange the secret key. It's possible to, after exchanging the secret key to have, for example, symmetric encryption, okay, like DES or AES. So the Diffie-Hellman algorithm is robust because it's based on the difficulty of computing the discrete logarithm. Remember, I already presented the discrete logarithm. So the idea here is that if you have a primitive root of the prime modulo p, then the number a mod p, a square mod p, a to power p minus 1 mod p are all distinct and consist of integer from 1 to p minus 1 in some permutation. So in this case, based on this, for any integer b, and a root primitive a of prime number p, we can find a unique exponent I such that b is the remainder of a to power I mod p. So this is the idea. So based on that, we say that I here, the exponent I is referred to be the discrete logarithm of b for the base a mod p. It's like the exponential log, but here we specify that we work with discrete logarithm. Okay, so here a to power I will be b mod p, given that a is a primitive root of prime a, p, of prime number p, and b is an integer. So in this case, the unique exponent I, we have this unique exponent, and the I itself is referred to be the discrete logarithm of b for the base a mod p. Okay, so it's the discrete logarithm of b for the base a. We call it discrete logarithm of b for the base a is equal I. Okay, so it's very important problem, well-known problem, because it's very difficult. And the idea here is that if you have a and I, you can calculate a to power I, okay, and after that you find the value of b. And this is typically what we can do. But if you have a and you have b, it's very difficult to find I, and this is the discrete logarithm problem, okay? So using this, the idea here of Diffie-Hellman is to exchange a secret key. So what Alice and Bob will share, so you have a kind of prime number p and an integer number q, alpha, sorry, such that alpha less than q. So both are aware about alpha and Q. Alpha and Q, alpha and Q, those are public information for them, okay, or what we call public numbers. Okay, so alpha is selected such that alpha is a primitive root of Q. Okay, and in this case, Alice will select or will have a private key, which is the secret key XA. It's the secret key of Alice, such that XA is less than Q. And Bob also will select a secret key B such that XB is less than Q. At this level, Alice will generate YA equal alpha to power XA mod Q. And Bob will generate YB equal alpha to power XB mod Q. Okay, so now Alice will keep XA secret, but will send YA to Bob, and Bob will keep XB secret and will send YB to Alice. So when Alice received YB, Alice will calculate the secret key, that is YB received from Bob to power XA mod Q. And Bob will calculate YA to power XB mod Q. And in this case, one can see that the key is the same because it is alpha XA XB. It's the same calculated at both directions, but it is calculated, and each of them keep the secret key without any disclosure. Okay, so this is the main idea here. So K is equal YB to power XA mod Q. It's alpha to power XB to power XA. So it's alpha XB XA, and it's alpha XB XA. From the other side, this is the secret key calculated by Bob. It's YA-XB, it's alpha XA XB, alpha XA XB, it's the same. So we are sure that the result at the two sides is the same secret value. Okay, so the idea here is that it's very difficult if you have YA and alpha and the Q, it's very difficult to deduce XA. That's the difficulty of discrete logarithm problem. The same for Bob. If anyone have YAB, which is public, sent to Alice, for example, and alpha and Q, it's very difficult to deduce or to find XP. It's computationally different. It's very difficult to compute it. Okay. So this is the security of Diffie-Hellman. As we said, the difficulty of this Diffie-Hellman is in the fact that while it's relatively easy to calculate exponential modulo prime, it's very difficult to calculate the discrete logarithm. That's what we say the difficulty. And here we just take an example. Okay, let's say we want to take Q equal 353 and a primitive root of 353, which is, for example, 3. In this case, let's assume that Alice select a secret key 97 and Bob select a secret key, which is 233. Then how to compute the public key, the secret key, and the exchange secret key. So YA equal alpha to power XA mod Q, it's equal 3 to power 97 mod 353, it's equal 40. And Bob will compute YB, which is alpha to power XB mod Q, and it equal to 148. So at this level, Alice will send YA to Bob, and Bob will send YB to A. And then the both will calculate key following the same as we presented before, and they have the same secret key 160. Okay, so here, if an attacker know, for example, Q, alpha, YA, and YB, okay, let's say, for example, he will focus on one of them, it would be possible by brute force attack to determine the secret key. Why? Because we are working on a small number value. It's not a big number value. It's a few bits. Okay, because if we want to work with, for example, 2048 bits, it's really a very large number, and the computation as a brute force attack will be very difficult. So in this case, let's execute the brute force attack, and in particular, let's go. The attacker would discover the solution. So the attacker would assume that he know 40, okay, and he know Q. So he will try to find what's the value A such that A to power, 3 to power A is equal 40 mod 353. So this is the discrete logarithm problem. In this case, the attacker will try all values of A in order to reach the right equation. So, and the other one is what's the value? 3 to power B equal 248 modulo 353. So the brute force attack here is to calculate the powers of modulo 3 modulo the power of 3, so 3 to 9, 81, and so on. All of them modulo 353, okay, in order to find at a certain time to stop, either at the value of 40 or at the value of 248. And in this case, if we try them, in this case, we find that it's reached with the secret key of A equal 97 in this case. Okay, and we can, which is the secret key of A of Alice. Okay, as we said, with large numbers, the problem become very difficult. It's really in practice we cannot do it, because with high huge number like number with 2048 bits. Okay, so this is the security of Diffie-Hellman. That's why Diffie-Hellman is used to exchange the secret key, but we work with large number. Okay, with large numbers. Another attack is possible even with large number. As I said, the large number avoid any brute force attack, but here is what we call man in the middle attack, where in this case we don't have an authentication between the participants. So this will generate a vulnerabilities. And in this case, let's say Alice, as we said, generated the YA. Okay, I will not repeat private key all step. You are aware about them. But when sending YA to Bob, okay, Bob don't have any, let's say, mechanism or any tool to verify that Y is coming from Alice. Okay, and also when Alice send it to Bob, Alice is not aware about if a third party or a third person or an attacker could take also this value. So in this case, an attacker will take YA, and then he will try to generate two private key, KD1, XD1, and XD2. XD1 will be used for one, and the XD2 will be used for the other, using the same idea as a receiver from Alice, and the other one as a receiver from Bob. And in this case, he will send, when receiving YB from Bob, he will calculate the other value, he will send YDA. So in this case, Alice will receive YD2 from the Darius, but Alice, we assume that it is coming from Bob. And from the other side, Bob will receive YD1, and Bob in this case will consider that this is coming from Alice. In this case, the exchange is done between Alice and Bob, but all exchanges will be done through Darth, and Alice and Bob are not aware about this. So in this case, the secret key, we have a secret key generated between Bob and Darth, which is K1, and another secret key generated between Alice and Darth, which is K2, but Alice is not aware that this key is with Darth and not with Bob. And also Bob is not aware that key 1 is done with Darth and not with Alice. So this is really the problem of man-in-the-middle attack. So how to avoid this problem? As we will see, Bob should authenticate the message coming from Darth to be sure that if it is from Alice or no. And in this case, we should use what we call digital signature and certificate, and we will see them in the next chapter or the in 2 chapters, okay? After 2 chapters. So to avoid man-in-the-middle attack, we can use digital signature, for example. But for instance, if we are using Diffie-Hellman without the authentication phase and or digital signature, it is possible to be attacked using man-in-the-middle attack. Okay. So was the part related to Diffie-Hellman. Let's see another a crypto system, which is also a very interesting crypto system. It's similar to the one. It's closely related to Diffie-Hellman, but it's used also as one-time key and to encrypt and decrypt the message. And also the security of El-Jamal is also based on the difficulty of computing discrete logarithm. And here, as we said, if we want to recover, we want to calculate as in Diffie-Hellman. Okay. So what's the difference here? The difference here, how we encrypt the message and how we decrypt them. So let's see. We have 2 global parameters like Diffie-Hellman, Q and alpha. They are public. And as we said, alpha is less than Q and is a primitive root of Q. And when Alice will generate the key, Alice will generate a secret key XA and will calculate YA equal alpha XA mod Q, similar to Diffie-Hellman. And here the public key will be Q alpha YA, and the private key is A. Okay. Also, if Bob want to encrypt a message, okay, and to send this message to Alice, how Bob will use it. So as we said here, it's really close to Diffie-Hellman, but it's used to encrypt and decrypt message. So in this case, if Bob want to send a message to Alice, so Bob will encrypt this message with the public key of Alice. So how we typically, if we have a plain text, it should be less than Q because we are working modulo Q. And he select an integer, a random integer less than a Q, a random integer less than Q. And in this case, he will calculate K such that K equal YA to power small k mod Q. And we calculate C1 and C2, which is cipher 1 is equal alpha to power k mod Q, and C2 equal k, which is calculated here, times the plain text, okay, times the plain text mod Q. And the ciphertext of M, which is plain text, the ciphertext is C1, C2. So this is the way El-Jamal crypto system is working. So the encryption is to multiply the plain text by k mod Q, and k is generated, as we said, k equal YA to power k, and C1 is sent because we want to send this small key also. At the reception, Alice will receive C1, C2. C1, C2 is the encrypted text of the plain text M. They are encrypted using the public key of Alice. So Alice using his private key, her private key, Alice will calculate K. How to calculate K? Say 1 to power xa equal C1 is alpha to power k xa, okay? And in this case, alpha to power k xa, it's alpha xa and then to power k. And after that, m is simply C2 k minus 1 mod q. So the first step on the decryption is to calculate k, and after that is to multiply the cipher2 with the inverse of k mod q. If we want to see, we can do briefly the proof. So C2 is equal Km. So in this case, C2 is Km, or we can put it Mk if you want, Mk, K minus 1. So K minus 1, and we obtain M, okay? And how we calculate K? Because C1 is received, okay, C1 to power xa equal alpha to power xa, alpha to power k to power xa, and we said it's alpha to power xa, then to power k. Alpha to power xa is y to power k, which is k. If as an ya to power k. So in this case, we calculate k and we find the answer. So it's very easy in the encryption and also in the decryption. It's one also of the well-known crypto system. Okay. And as I said, the difficulty here is it's not possible if you have ya and q, even if you have k, to deduce the secret value xa, for example. If you have ya, alpha, and q, it's not possible to have to find the secret key xa. Another important crypto system is the elliptic curve. Elliptic curve, it's now will be widely used really because we are able to have important security level with relatively good size of values. Let's see them after explaining the mathematical part. So the elliptic curve, generally, it's really defined as an equation in two variables with coefficients, a simple elliptic curve, you know it. And for cryptography, the variable and coefficients are restricted to element in a finite field. We are working always in a finite field. And the result is really a finite abelian group abelian. You know that. And the typical, we are not working on all type of elliptic curve. There is a cubic equation. This is the typical equation that is used in crypto, which is y squared equal x to power 3 plus ax plus b, where a and b are considered as two values that are used for different cases. We could have different value of a and b. And we define, because we are defining the group, so we should associate the what are the additions and the multiplications operation that we are using, and what's the neutral element and what is the element. So in this case, we define the equation as follows. Okay, so typically here we can see for some example. Here in this case, we have a equal minus 1 and b equal 0. This is the one case of what we call e minus 1, 0. This one is e 1, 1. So that's why it's a set of e 1, 1 for a specific value of e. Okay. So in cryptography, as we said, we are interested in elliptic curve modulo prime number. So we will work always modulo P, and generally P is a big number. And if we want to construct the elliptic curve over prime field, okay, and typically over ZP, for example, where P is greater than 3, it's a set of all pairs or coordinate X, Y belong to ZP such that we have Y squared equal X to power 3 plus AX plus B mod P. So that's why here we are working with mod P. And as we said, we will define the additions and the multiplication and also the what we call the infinity point here. We consider the imaginary point of theta, where in this case we consider that we have this value, and typically in order to have this equation, the conditions they should be different from 0. This is the condition of what we call non-singularity. Okay, and typically ZP, you know ZP, it's the all integers less than P. You already maybe in algebra you did some exercise in semester 2 maybe regarding this part. So the identity point here, or the neutral element, if you want, the identity point here is theta, and typically theta is here. It's not on the curve, but we define it. It's an imaginary point, and it's as we said, it's the identity because P plus theta equal P equal theta plus P. So that's why P plus theta equal P. It's not on the curve, and we define also the additions and the multiplications, and we have the symmetric. So all points are symmetric over the x prime x. So in this case, if P is this point, minus P is x minus y. So P is xy, minus P is x minus y, because all points are symmetric over x prime x. And as we said, if we want to generate the additions, okay, typically if you want to add 2 points, okay, you can do it. For example, you have x and y and you can work on it, but in this case we have a specific case that if you want to add P and Q, so in this case you continue the line and it will intersection with the curve, and you take the symmetry of this one. So this point is P plus Q. So this is the geometric interpretation of the addition operation. It's possible to use it. It is possible to do it using coordinate x and y. But here we are making the interpretation, the geometrical interpretation of the figure. And if you want, for example, to add P and Q here, okay, it will be here. If you want to add here, and so on. So it's possible. You complete the straight line, and when you have the point intersection with the curve, and you find the symmetry. Okay. So the geometric interpretation of the addition operation. So you draw the line through P and Q, and you mirror the third intersection of point and draw the line with the elliptic curve along the x, okay, as we said. If, for example, P equal Q, in this case, you are working on the same point, it's P plus P. In this case, it's like you are doing the tangent here, and this is the intersection point, and you take the symmetric over x prime x, and this will be P plus P equal to P. Okay. If I want to find 4P, which is 2P plus 2P, this is the point 2P. I should take the tangent here. It will be here, and the symmetric, this is 4P, and so on. Okay. So we have here the addition operation. If we want to use the let's say the addition operation using the formula, it's possible. Let's say that we have x1 for the first and x2 for the second, x1 for P and x2 for Q. So in this case, if you want to calculate x3 and y3, which are the coordinate of the additions of P and Q, it's possible to use those formula. X is equal this and y is equal this, with the term S is based on those formula. It's this form if P is different from Q, which is in this case the addition, classical additions. And if P equal Q, we follow this equation. This is because here we are taking the tangent. It's like we're doubling that point. So anyone can verify this. Those are based on the coordinate equations. Okay. So having this is algebra till now. How we can use them in elliptic cryptography, elliptic curve cryptography? Why we are using those arithmetic equations in cryptography? So we say consider the equation Q equal K times P, which means that Q is the point that we obtain after multiplying P K times. So in this case, we say that Q and P are 2 points belongs to the group we are working with parameter A and B and with the prime number P, and K, the multiplicative number, is less than P. So typically, as you said, it's relatively very easy to calculate a Q given K and P, which means that if you have the point key in this operation, at each time you have P, you can have 2P, 4P. If you want P plus P, you can continue them and so on. So the operation, it's very easy to find them. However, it's very hard to find K given P and given Q and P because we are working modulo P here. Okay. And this is what we call discrete logarithm problem for elliptic curve. Remember that the discrete logarithm that we presented before was in general and not specific for the elliptic curve. Here, when we want to talk about the problem to find the value K here, this is what we call the discrete logarithm problem for elliptic curve. Okay, this is an example. And if we want to take, for example, we are working with P equal 23, mod 23. Okay, this is the group defined by the equation y square equal x3 plus 9x plus 17 mod 23. Okay, if you want to find what's the discrete logarithm K of Q equal 4, 5, where P equal 16, 5. So the idea here is to calculate the brute force attack. Here to calculate the P plus P, it's 2P. We obtain this point. And after that, 2P plus P, they are 2 points. 3P, 4P, 5P, until we reach 9P. And we say that in this case, K equal 9 because we find the Q here. Okay? So in this case, because 9P is equal to the discrete logarithm, Q to the base P is K equal 9. As we said, this is a simple example just to let you understand the concept, but K would be so large as to make the brute force approach infeasible. And here in this case, it will be very difficult to attack and to conclude and to find this value of K if we are using so large number. Okay, so this is the idea here. If we want to use the elliptic curve crypto system, we can use them for key exchange and following Diffie-Hellman. So the idea here is that we want to select, okay, we have the generator, we have the elliptic curve parameter, they could be public, and we have a point G, which is the point on elliptic curve, okay, and typically is the larger value, okay, or the large value n, and we select the private n1 less than n and the public key PA such that PA equal NA times G. here we can see that NA is the secret key, G is the point, and the PA is the point. It's like here it's P, here it's Q, and this is the value small k that we want to know. And in our case, NA is the secret key, the PA is the public, and G is the point on the elliptic curve. Okay. And B also could select NA and B, sorry, less than N, which is the private part, and calculate the public PB equal NB times G. And after that, they send the PA to Alice, and Bob will receive also from Alice PA. And in this case, he will calculate K equal NA times PB equal NA. PB is NB times G, and also here we have the same key, which is NB times NA times G. And in this case, we are using Diffie-Hellman approach, but the key exchange is based on the elliptic curve problem. Okay, this is one of the well known, and it's really very difficult to compute K given G, and it's really very hard. Okay, so that's why elliptic curve Diffie-Hellman key exchange is well known. As we said, this also is vulnerable to to man-in-the-middle attack if we don't have authentication. But it's very difficult to make the brute force attack. Okay. The importance of elliptic curve is that with elliptic curve, we are able to have a high level of security with, let's say, relatively key size less than RSA. If we want to take, for example, RSA, with RSA 100, 1040 bits, okay, we could have the same level of security of elliptic curve with, for example, the range of 200, for example. That's why now with IoT system and with the new modern system, all of them we are using elliptic curve because we are able to reach, for example, here with RSA, we need 4048 bits as a key size, but in elliptic curve, it could be, for example, 250 or something like this. So with elliptic curve, we are able to reach the same level of securities as RSA, but with less number of bits. And that's why it's very important to see the computational effort. This is what we call computational effort. That's why I'm talking about security, because we consider now that RSA with 2048, it's really secure. It's computationally secure because it's not easy to compute to make it a brute force. So the same effort, because as you can see, the discrete logarithm for elliptic curve is much more complex, and that's why we can have better security, but with less key size, and so on. If we want to take, for example, elliptic curve with 512 bits, it's comparable to RSA with a huge bit size. Okay, so this to complete this part, those are the important asymmetric crypto system with public private, and it's very important for you to review them. And if you have any question, please contact me for that. We will try to make some exercises. Okay. Maybe before continuing, we talk about Chinese remainder theorem. This is just a simple, as I explained for you, the Chinese remainder theorem states that if you want to you have a number, let's say x, and you don't know x, but you are able to know that what's the let's say the residue or the modulo, the rest of x over different value n1, n2, and 3 such that n1, n2, and 3 are co-prime positive number. So if you are able to know A1, A2, and A4, that's why reminder, they are the reminder. Okay, in this case, if you want to put this system, the Chinese reminder theorem states that this system has a unique solution, which is n, it's a unique solution modulo n. Okay, you can find x, and x is unique, okay, for a system modulo n, where n is the multiplication of n1, n2, n and so on. Okay, and remember that n1, n2, and 3 are co-prime. Each are pairwise co-prime. This means that each two are prime. Okay, co-prime. So here, this is the theorem, and there is a way, a general construction to find the solution. And here we say that if you know, so you know A1, A2, A3, A4, and you know N1, N2, and 3, and N1, N2, and 3 are pairwise co-prime positive integer, and you want to find X. This is the problem. So the solution is that you compute N, and for each I, you compute that yi equal n over ni. Okay, so this means that just you remove the part ni, and after that you compute zi to be yi minus 1 modulo n, which is the inverse, of yi modulo n. Okay, because they are pairwise co-prime, so zi is valid and exists. And after that, in order to find x, you just need to sum from I equal 1 to k ai yi zi. Ai is already given here. Yi you calculated it here, and zi is the inverse of yi modulo ni. Okay, and this will give the unique solution of the system. And I will give you a simple example. Let's consider that we want to find x such that the remainder of x modulo 7 is 5, the remainder of x modulo 3 is 2, and the remainder of x modulo 11 is 9. And we can see that 7 and 3 are coprime, 3 and 1 and 11 are coprime, 7 and 11 are coprime. So in this case, if you want to follow the Chinese remainder theorem, say that this has a unique solution. And this unique solution will be find modulo n1 times n2 times n3, which is 231. So as we follow, so we can see that we should construct yi, which is equal to n over ni, which is y1 equal n over n1, it's n2 times n3, it's equal 33. Okay, and after that we should calculate z1 equal the inverse of y1 modulo n1, which is the inverse of 32 modulo 7. This means that what's the number that we multiply by 33, and the remainder will be 1 modulo 7. Okay, so the result will be equal to 3, because if we multiply 3 times 33 modulo 7, it will be equal 99. Okay, 99 equal 1 modulo 7, so that's y is 3. Okay, and we calculate also y2 following the same idea, which is n over n2, it's n1, n3, and y3. And then we calculate z2 and z3. Having those, we calculate x equal sum from I equal 1 to k. In our case, is 3. From I equal 1 to 3, a1 y1 z1 plus a2 y2 z2 plus a3 y3 z3, and modulo, we are talking modulo 231, it will be equal 152, and this is the unique solution of the system. Okay, this is the Chinese remainder theorem. Okay, and it's an important also part to review. Okay, so let's move to the exercise. Okay.